Hi, everybody, and welcome back. So last time we talked about, we gave a brief overview of the five main functions that are important for control flow. So we've got if and else, we've got while and break, and we've got for. And these are the core foundational expressions of core foundational computations that a computer will do deep inside of the computer. And we have access to some of these operations in R as well, but most of the time we're not going to use them because we have what are known as higher level functions or higher level abstractions of these five fundamental building blocks of computer code. But we said that basically everything that your computer does, you don't see it, but basically everything that a computer does deep down is dealing with either if and else, while and break, or for. Like one of these options here, and these kind of go together. So if and else go together, while and break go together, and then for loop is just kind of off by itself. But it's a for loop is related to a while and a break statement. So let's talk about a for loop. In the if else statement, we had one single uno logical value that would resolve to true or false. And if it was true, we did one thing, and if it was false, we did something else. Okay. Sometimes what we do when it's false is we do nothing. That's okay. That's something that we can do. We can do nothing. For loops, however, they are going to operate over a vector of some kind. Okay. Now, sometimes this is an atomic vector. Sometimes it's a non-atomic vector. But usually, the for loop is going to operate over a vector of integers. Okay. Now, at the abstract level, we can make a for loop operate over a list, which would be a non-atomic vector. But the way that we're going to do that is by using the integer position of the list. So when I said earlier we can make for loop work over basically any kind of vector, it's because if you remember back to the lesson on vectors, vectors are ordered collections of objects. And if they are ordered, then therefore the elements of the vectors have positions. So if I have an ordered collection of objects that are 10 items long, there will always be a seventh item. Okay. And so that means that I can perform a calculation that says operate from the first until the seventh item. If I have at least 7 items, I can do that. And the reason that we can do that is because, again, vectors, whether they're atomic or non-atomic, are ordered collections of objects. And again, ordering means that there is an index to that order. That's what a for loop works on. A for loop is going to work on the index of a vector. Okay, so let's take an example here. So I have an atomic integer vector here of 1 to 10. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the structure of the for loop is we write the command for, and then here we say for this condition, the condition being that there is an index of all the vectors of all of the elements in this vector, basically. So here's an index, and usually we use I or J. If I'm working on the rows of a matrix, sometimes I will literally use the word row, or I'll type the letter R. So so if I'm operating on the rows of a data frame, or rows of a tibble, or rows of a matrix, then I'll say for R in the rows of this rectangular data. Sometimes if I'm working across the columns, I'll say I don't want to use C because the C function is for concatenate, but I'll type COL. So for column in, and then here's the set of the indices of the columns. Then notice here, I've got my curly braces again. That means we're dealing with an expression. Okay. Technically, we're dealing with an expression over here as well, but this is the expression that we want R to resolve. We say, okay, for every single instance or every single unique value of J, every single time that I'm going to get a new J from 1 all the way up to 10, I want you to take that value of J, I want you to add 1 to it, and then I want you to print the value. So when J is equal to 1, 1 plus 1 is 2, and R prints 2. Okay. All right, now there's a couple of things to extract here. Notice that each time R prints a number, I get a new atomic integer vector. that this counter, see this resets every single time. What that means is that the for loop is creating 10 different objects. We started off with one object. We started off with the atomic integer vector from 1 to 10, and we ended up with 10 atomic integer vectors, each of length 1. Okay, it's very important to understand that the for loop is going to often create new objects. Many times you'll be creating new objects or whatever, because an expression can create a new object. It's going to happen independently. Well, let's see, somewhat independently. Like the calculations that happen inside of a for loop, a lot of times you can make them depend on the calculation that happened before, but usually you make it depend on the calculation that happened before through this J or through this index increasing. And if that doesn't make a whole lot of sense right now, hopefully through the examples, that statement will make some sense. But what we do need to understand here is that this for loop did not create a new atomic vector of length 10. So I started with an atomic vector of length 10, and the action was to add 1 to each element. But I did not end up with an atomic vector of length 10. I ended up with 10 atomic vectors, each of length 1. Okay, this is a very important distinction. All right. Now, the reason why we're almost done with the entire semester, we're on lesson 11 of 13, and you've never seen me do this before, is because R is already vectorized. If I actually needed to do this, I can literally just type, give me the atomic vector from 1 to 10 and add 1 to it. In this case, I start with an atomic vector of integers of length 10, and I end with an atomic vector of integers of length 10. Actually, because I didn't put an L here, I might end with numeric. But notice the difference here. I start with an atomic vector, one atomic vector. I end with one atomic vector. But here, I started with one atomic vector. I ended with 10 atomic vectors. Okay, very important distinction here. So the reason that we're going to be talking about this is sometimes we do need for loops. Okay, most of the time, though, you're not going to use it because R is already vectorized. R already has the tools for you to do for loops built into it. And we're going to learn a lot more about that, especially when we get into this lesson called Per. The next lesson is all about using functions to do iteration so that we don't have to write for loops. And we get to preserve this vectorized operation here, where if you start with a vector, you end with a vector rather than starting with a single vector and ending with 10 vectors. Okay. A lot of times if you want to start with data of the same structure and end with data of the same structure, or there sort of be a mapping between that. If you remember when we went back to the lesson, one of the previous lessons, the supplement that was comparing dplyr to base R subsetting, one of the complaints that we had about regular data frames was that sometimes when you subset them, you got a data frame. Sometimes when you subset them, you got an atomic vector. So based on how you interact with this data frame, sometimes you get atomic information, sometimes you get non-atomic information. Similar complaint here with for loops. Sometimes you can write a for loop that you start with one atomic vector. Other times you write a for loop and you end up with a lot of stuff. Okay. All right. So let's move on and let's talk about why for loops are important. Okay. For loops come up whenever you need the calculation at one step in the index to depend on the calculation that happened previously. Okay. So this would be kind of like, think back in one of your classes that you took in undergrad. You might have had a class that you were allowed to skip the final exam if you had a good enough grade going into the final exam. Like if at the end of the last homework assignment before the final exam, you still had, I don't know, like a 94 in the class or something, or a 92 in the class or a 95, whatever the number was, maybe the professor had on their syllabus that like, okay, cool. I give you this option that I'm going to drop your lowest test grade or something like that. And that includes the final. So even if if you got a 0 on the final, that would be your lowest test grade. You would drop it. And therefore you could skip the final exam or whatever. Okay. The decision of whether or not you take the final depends on the grades that happened before. Okay. And even more so, the amount of effort that you spend studying for this exam here depends on the grade that you got here. Okay, so let's go back to the first assignment in the class, whatever this, some, I don't know, some history class or whatever. And you study really, really, really hard for the first homework assignment, the first quiz in history, and you just blow it out of the water, 100 across the board. And the teacher talks to you and like, wow, you did really, really well on that homework assignment. You must be gifted at this or something. And you realize like, okay, you know what? Maybe spending 10 hours studying for one quiz was a bit overkill. Okay. So that's going to inform the amount of effort that you spend studying for the next quiz. And you're studying for the next quiz and you say, okay, 10 hours was clearly too much. Let's see if I can get away with a similar grade at 5 hours of effort. So you studied for 10 hours for the quiz this time. Then this time you studied for 5 hours on the quiz. And on this quiz, you got a 99. Okay. And you're like, okay, so I spent 5 hours and I got a 99. Last time I spent 10 hours and I got 1 point extra, the 100. Okay. So clearly that extra 5 hours was not worth my time. Let's see if I can actually like, okay, well, I don't want to drop down to no hours because that doesn't make any sense. So the first test, I spent 10 hours, I got 100. The second one, the second quiz, I spent 5 hours studying, I got a 99. Let me see what I can get away with if I study for 3 hours. Okay. So the next time I study for 3 hours, and this time I got a 90. Okay. Like, all right, well, I don't like getting 90s. I want to get a little bit better than that. So I know that I need to spend somewhere between 3 and 5 hours studying for these quizzes. Okay. But you can see how your previous information, the knowledge that you gain from your previous experience, informs what you do the next time, and therefore informs the results that you got the next time. And then that informs what you get the time after that. And so then you say, okay, well, the next time I'm going to bump it up. I'm like, let's see if I can get away with like 3.5 hours. So you spend 3.5 hours, and that 3.5 hours, the 5 hours was way too much. 3 hours is not quite enough. Out of 3.5 hours, you're like, okay, I got a 95 on this quiz. I am happy with that. I am definitely getting an A in this class, but I'm not wasting all this extra time because the other 6.5 hours that I spent over here, if I can get a 95 with only 3.5 hours of studying, then the other 6.5 hours that I spent back here getting 100, it was kind of wasted because I'm going to get the same A whether I got a 95 or whether I get 100. Okay. But you're like 90. I want to give myself a little bit of buffer. And besides, 90 is getting close to A minus anyway. So let's just make sure we're staying at 95s. And so what's happening is the information, the calculation that you're doing in your brain for this time point depends on what happens in the previous time points. Okay, this is for loop based computing. Okay, so the way what you would say is for each quiz in the semester, I'm going to do an operation. I'm going to spend time studying based on the grade that I got in the previous quiz. So if 1 week I only spent an hour studying and I got a 70 on that quiz, clearly the next week I am going to increase the time spent studying back up to 3.5, maybe 4 hours, because I want to like overkill it. Like, okay, let me make sure that I make up for the fact that I got a 70 last time. I maybe even go talk to the professor. I'm like, oh, I'm so sorry, professor. I only had an hour to spend on the class. And so I got a 70. I promise you I'll do better next week, something like that. But the decision that you're making at this instance depends on what happens before. That is the purpose for using a for loop, is when you need computing or an expression or a decision or some computation at this instance to be influenced by what happened in the instances prior. And a good example of this is the Fibonacci sequence. So the Fibonacci sequence, if you don't know, is the sum of the two integers that came before it. It starts at two ones. So I'm gonna create an empty vector of length 50. So that's what this is. So repeat NA underscore integers so we remember that I'm using the NAs specific to integers because I'm going to fill this thing with integers. And I want 50 of them. And the first two, so I need to, whenever we're dealing with for loops like this, you usually have to initialize it because you need what happens next to be dependent on what happened previously, which means you already have to have what happened previously inside that vector. So the first two entries of this vector, I initialize as ones, and then therefore I start at 3 because I've already got 1 and 2, and I say go from 3 to 50. So the third entry of the Fibonacci sequence should be the second entry plus the first entry. And so we get 1, 1, and then right here, 1 plus 1 is 2. And then the fourth entry of the Fibonacci sequence should be this 1 plus this 2. So right here, I've got the third entry of the Fibonacci sequence, which is the 2. And I've got the second entry of the Fibonacci sequence, which is a 1. And then that one's a 3. Notice that this grows very, very fast. It grows to the point that we run into something called integer overflow. The numbers are so large that R says, I don't know what to do with these, so I'm just going to give you NAs. Just be aware of that, like that we can deal with numbers that are so big that R doesn't know what to do with them. Usually the way we get around this is by taking like a log, like a base 2 logarithm or a base 10 logarithm. And we say, okay, well, we're going to work in the logarithm space because they're much, much easier to deal with very, very large numbers. Okay, so I think what I'm going to do is we're going to leave you with this exercise and then come back and talk about the while loops and how to escape while loops, which is called a command called break. Okay, so I want you to do this exercise and I want you to go back and kind of understand why this code did what it did the way it did. So remove the print statement and start experimenting with this for loop and see if you can wrap your head around what's going on. Okay, see you next time.